So, we will first introduce the main topic today, and then followed by introduction of the project Solve itself, and also especially on theme 3 and theme 6, enhanced PV system, and also planning for large scale PV expansion. And then followed by the four main speakers. And unfortunately, the loss of speaker Phil is sick today. So, and Andres Tuchers will present for him. Then we'll conclude with the comments and conclusion finally. So that's agenda for today. Here we can say a few words about ourselves, though about the speakers or moderators today. So I can start myself. So my name is Xinxin Zhang. I'm professor in energy technology from Dalarna University. So I'm the co-leader of the theme 3 in the Solve project. So I go to Joachim Munkhammar, please.
Yes, Joachim Munkhammar. I'm an associate professor at Uppsala University. I'm also part of theme 3 and 6, but co-leader of the theme 3. Yes.
Thank you, Joachim. And I'll go to Santiago.
Hi, good morning. My name is Santiago Valencia. I'm a PhD student in Team 3, and I study optimization of PV systems and some life cycle assessment also.
Thank you. And we go to then Andres, please.
Hello, everyone. My name is Andreas Theocharis, Associate Professor at Kassel University in Electrical Engineering. And I'm also in the team of theme leaders in Solve, in theme number 6.
Thank you. Then Mohammed, please.
Hi, my name is Mohammed Kubar, a PhD student in my second year at Uppsala University at the Division of Civil Engineering and Built Environment. I work on optimal planning for large-scale solar energy with combination with battery storage.
Thank you. And then Reza, please.
Hi, everybody. Good morning. My name is Reza Fahrizal. I'm currently a postdoctoral researcher at Melardalen University, previously a PhD student in Uppsala University. Also, at the final year of my study, I also contribute in software.
Thank you. And the last, we go to Joachim Widén, please.
Yes, Joachim Widén. I'm a professor in civil engineering and built environment, and also one of the theme leaders for theme 6.
Great, thank you. And then, since the time is limited, we can't go through each participant, unfortunately. So we just end up with the main introduction of the main speakers. So then, here, Joachim, then floor is yours. Then you can talk a bit about the source there.
Thank you. So I'm going to start off with a few words about what Solve is as an introduction to everyone. Solve is one of a number of competence centers which were approved and funded by the Swedish Energy Agency. These competence centers are supposed to strengthen collaborations between companies and public agencies, etc., and academia. So among these different competence centers, all focusing on energy, we have Solve, which is then focused on solar energy. You can go to the next slide. We have quite a lot of partners in Solve. We are 6 universities and research institutes: Uppsala University, RISE, Dalarna University, Mälardalens University, Swedish University for Agricultural Sciences, and Karlstad University. And as you can see here, we have quite a big list of companies involved and also co-funding the center. We can go to the next slide. So this is the structure of Solve, the organizational structure. We have in the top of the pyramid here, we have the Solve board, which is making decisions about the center. We have board of directors and an executive committee. But then most of the research and development work is done in these different research themes. So we have 4 topical research themes, you can say, and then we have 3 cross-cutting research themes. So you can see some of these are focused on different things like advanced technology, building integration, enhanced PV systems, and land sharing. These are like the main topical themes, and then these cross-cutting themes are economics and business models, planning for large-scale PV expansion, and sustainability and life cycle assessment. And today then we are focusing on theme 3, which is on enhanced PV systems, and theme 6, which is planning for large-scale PV expansion. So we will showcase some of the research that is done in these themes. And you can also see here we have a PhD school connected to these different research themes. And I should really say that the PhD students are the ones doing most of the actual work in here, and they are also the ones who are going to speak. Yes. Yeah, so these are a bit more details on the different research themes. I won't go into the details on everyone, but we can note here theme 3, which is represented here today, enhanced PV systems. So the goal here is to optimize the role of PV in new complex energy systems and on different spatial and temporal scales. So Xinxing and Joachim Munkhammar are leading this theme. And then we have theme 6, which is planning for large-scale expansion. So here we really try to find ways of making a smooth expansion of PV technology in Sweden. Andreas and I are leading this theme. And as I mentioned, here we have the PhD students who are doing most of the actual research work. So they are then connected to the different universities. They all have supervisors from the universities, but also from the different companies to have this industry connection. Yeah, I think that's enough for my overview. So I will hand over to Joachim Munkhammar to describe the theme 3.
Yes. Yeah, so theme 3 is enhanced PV system. And I mean, it's a stated aim of optimized PV system at local community level with connections to buildings and grid city scale. So you could see it as sort of between the level of on building, like individual buildings, up to the scale of like entire cities. So it bridges sort of the gap between that, the communities. So it's largely based on optimal system design. They try to find optimal system design by data-driven analysis. You want to maximize economic return of PV systems, but you also want to look into, for example, the global warming potential of systems, as we will hear more about. And there's also a challenge, of course, to investigate the control of power system distribution, like how does PV affect the local system. And an important thing here is also to connect battery and hydrogen storages, both in terms of economical performance, but of course technical being a thing. And it's mainly for the end user in some sense, to improve sort of the functionality, the flexibility, transparency, and economic return for the actual PV user in the community or in the houses that are considered. Yeah.
Thanks. Now, Andreas, please.
Yeah, as regards theme number 6, we work on large-scale solar power integration in the energy networks. There are different types of solar systems in different scales and contribute in different geographical areas and different levels of the electrical grid. So our aim is to explore how this PV development in Sweden can be guided by a top-to-down approach for optimal energy utilization. To do that, we have some objectives, like, for example, to conduct the hosting capacity studies to determine how much power, solar power, we can inject in specific points in the electrical grids. We are aiming also to forecast energy production and consumption of grid-connected users, aiming to schedule in an optimal way the energy transactions. We also investigate synergies for solar power with other forms of energy, like stored energy, hydrogen production. There are cases, for example, where one can produce biofuels and stuff. To do that, we use several methods and tools, such as big data, statistical and stochastical mathematical approaches, machine learning, that is a trend, quite a trend nowadays, and systems optimizations. If we go to the next slide, in both theme 3 and 6, the interest overlap coincide in main locations, and of course are also driven from the companies and the national organization and national interests. Just to name a few, we're interested about, as I said, storage, batteries, electric vehicles, charging, electrification in general of the transport sector, one can say, grid ancillary services, smart energy control. In order to cover these topics, these interests, we have dedicated PhD students projects and master projects occasionally that our researchers collaborate closely to each other. And today we are going to present some of these projects, especially these projects that are run from our PhD students. So I think now, Xinxin, the floor is yours to continue. Students, maybe.
Yeah, thanks a lot, Andres. And that's it for a very short introduction on the whole, background of the webinar. So then let's start my presentation. And meanwhile, of course, we plan to have 1 or 2 questions after each main presentation. And so you should be able to ask questions if you have any. And then meanwhile, it will also put your questions into the chat if you don't have a chance to ask. So please, Santiago, if you can share your presentation.
Yes, thank you, Xinxin.
Yeah.
Yes. Put it down. Okay. So can you look at my screen now?
Yes, perfect. Please go ahead.
Yes. Thank you. So yes, as you know, my name is Santiago, and I started my PhD with a review on the coherence of strategies for optimizing photovoltaic systems. This was presented 2 days ago in Cyprus, in Eurozone, and it was well received. Even when it was critical, it was well received by the academic community, which was really nice. So first, I started asking me why to research on optimizing photovoltaic systems. I wanted to have a starting point, a good starting point for my PhD, so I started asking why. And what I found is this kind of phrases or concepts, they appear in the first or second sentence of every paper that I was reading, or what it looked like every paper. It's not like every paper, but it looked like to me that sense. So, okay, I share this with many people. I share these thoughts, and I know the importance of this. Things like greenhouse gas emissions, carbon emissions, global warming, climate change, environmental sustainability, Paris Agreement, pretty much everything around climate change and some more general environmental sustainability concerns. So all of these things can be called motives. And since I am doing optimization, I will need to define optimization objectives as part of my optimization functions. And finally, I will have to pick key performance indicators to assess the performance of the systems that I will optimize. There was studies on the motives. So people asked stakeholders, what are their motives around PV systems? Mostly the motives were environmental sustainability, pretty much what I just showed. Also, there were some economic concerns and so on. There are also reviews on optimization objectives. So they told you which kind of objectives can you use depending on the type of optimization, which kind of constraints can you use, and so on. And there are also reviews on key performance optimizations, indicators. So there are reviews that tell you, okay, you can use this indicator to assess economic performance, or you can use this other to assess how much energy are you using, and so on. But there was no review around the coherence between these three things, which was what we studied. So the motives could lead to optimization objectives. So you define your motives, then you set your objectives, then you measure your objectives with your key performance indicators. You measure how close you are to your objectives. Then kind of this strategy appears, a framework for optimizing. So first motives, then optimization objectives, and then at the end, you see how close are you to achieve your objectives, how close, or which is the best response to your function. So first, motives, why are we doing this? Second, how are we doing the optimization? Which variables are we picking to minimize or to maximize? And the third one, how do we know that we are achieving our why? Some quantities that gave us some sense if in fact we're getting closer to our motives or in fact we're getting farther away. So for this, we analyzed several papers with photovoltaic systems, with storage, with optimization in buildings in the Nordic countries. We reviewed around 349 and 50 papers at the beginning, but at the end, we filter out and we end up with 36, which we study deeply. So the type of indicators that we found technical, environmental, and economic indicators, mainly. So there wasn't any specific social indicators. There are some well-being indicators that are integrated, in this case, in the technical. We group them in the technical, but specifically like social impact and those we couldn't find within the review papers. So first, let's start with the economic indicators that we can use. Main one, operation cost. This is usually when you optimize the operation of the system, the energy flows. So how the energy flows into your system, whether you storage or you control your demand or this type of operation optimization. There is another one, which is levelized cost, which also involves the investment. So you end up with a number per kilowatt hour or per unit of energy, other units, but usually it's per kilowatt hour. So you end up with euros per kilowatt hour or crowns per kilowatt hour, so on. Payback period, how fast am I going to get my money back? How many years will it take me? In this case, we found simple payback period, which doesn't include interest rates, and and payback period, which includes interest rates and the value of money over time, which I think is more accurate. Life cycle cost, so it's taking all your codes and bringing it into the present, and you have your life cycle cost in one amount. So you get to compare different costs of different systems, options. Net present value, am I losing money or I am winning money in the long run? If it is higher than zero, you're winning. If it is lower than zero, you're losing. It's taking all your positive and negative flows into the present, using interest rates and all these things that and rates for electricity and so on that help us bring those values to the present. Third one, investment cost. This one, sometimes they include interest rates, sometimes they don't. So yeah, this one didn't look so good. Total cost either. So yeah, investment cost. So these are not so good because they are not as comprehensive as the other measures. So they can be a bit misleading. Profit, which is the absolute number of profit, and return on investment. So here, from this personally, according to what I read, net present value and return on investment, I would say, are are very good. Also levelized cost, because this allows you to compare with other systems. What if I get the electricity from this other system and so on, or the heat? So I will say these three. Also, payback period is very easy to understand and to share with other people. So it might be good also. So technical indicators, self-sufficiency, how much of the energy that I use am I producing, self-consumption, how much of the energy that I produce am I using, so it's different. Energy efficiency, how much, which is the percentage of the efficiency of my system or my storage or in general. Energy storage. For energy storage, there are other variables further than efficiency. For example, degradation in batteries, thermal depletion in thermal storage, in big thermal storage, and others. Others, as I told you, well-being indicators such as thermal comfort, daylight, and so on. And others that are in communities, energy sharing, for example. And finally, this very small portion was dedicated to the environmental indicators. Total greenhouse gas emissions in operation and greenhouse gas emissions per unit of energy during the operation. They have different names, different things, also different standards for measuring greenhouse gas emissions. The most common is global warming potential, which measures the potential of global warming as a carbon CO2 equivalent in the point of 100 years in the future. However, there are several other ways to measure the environmental impact. There is water use, ozone depletion. There are many ways, and we just found this within the literature that we study. So we think we have a lot to do on this regard. One thing that we found is that the environmental impact is only considered during the operation, which might be also misleading, because you don't include the material extraction and manufacturing of the PV, which requires a lot of energy, a lot of resources to produce, and also the end of life, if you recycle it, if you disposal, and so on. So yes, so here are the indicators again. And you can have several motives, several indicators, or these are not exclusive. You can mix them. You can use multi-objective optimization to find several solutions, and you get to pick the one that you want. So yes, you can mix them. So here, the motives. So what people are intending to do, or what they state in the introduction that is the aim or the context for their solution. So 75% of the papers had environmental motives, technical motives, 94. Technical motives usually refer to the mismatch between production and demand. That's quite a challenge, and many authors address it and knows about it. And economic, they used to be very low motives, or not so many papers that had motives in the past, economic motives. But during the recent years, this has grown a lot. Economic volatility, for example, of the interest rates, economic volatility of the energy prices, and so on, has become a bigger issue now. So that's why these motives increased recently. The objectives that they use, so variables that we would like to minimize or maximize. 8% assess environmental impact or try to minimize environmental impact, which is very low compared to the 75 that says that they are going to reduce the environmental impact. 77% optimize technical variables such as self-consumption, self-sufficiency. In this case, self-sufficiency is also sometimes referred as solar fraction also. So just for you to have some reference if you have other ways of calling it. And 89% of the articles that we study economic optimization objectives. So they put as objective minimizing payback period, or minimizing cost, or maximizing net present value, and so on. key performance indicators that they use at the end to measure what they did, how well did they perform. 11% of the papers assessed environmental indicators, basically what we saw earlier, global warming potential, carbon emissions, or however they call it. 94% of the papers measure with technical variables, and 92% of the of the papers measure the results with economic variables. So we can see an imbalance here. Many of us are aiming for environmental reduction, impact reduction, but we end up measuring mostly technical and economic. So what we need is just increasing this. So yes, this makes me wonder, are we walking blindfolded towards our sustainability goals? Are we aiming towards something but measuring how close we are to that goal with other measurements that perhaps are not as precise or as coherent with the goals that we have? We need everything. We need something that works, that is economically feasible, and that is environmentally feasible. And we have the tools to do it. We have multi-objective optimization and certain algorithms that can help with that. So most of the articles show environmental motives, but only a few aim to improve or quantify them directly. So what is next? So now I have found this. So I think we need more comprehensive and coherent studies for optimizing PV systems. And I think we know we need a life cycle approach for the optimization with environmental variables. What happens with the environmental? So one question might be that I'm already addressing now with some models. What happens with the environmental indicators if we only optimize for technical and economic objectives? So what's going on behind all these papers with the environmental impact? So I can do a model and optimize for technical and economic objectives and measure what happens with the environmental indicators. Are they better? Are they worse? So this is still an open question. We have some previous findings, but it varies a lot. It has several different variables that change how it behaves. And another one is what happens with the life cycle environmental indicators if we only optimize considering the operation emissions. What happens if we only measure for what we see in the sky coming out from a plant? What happens if we don't see all the impact done behind or previously in other countries or in factories or during all those material extractions? So what happens if we don't include it? So those are the questions that I have now that I will try to address in the next few months, and I hope I will come with an answer for you. Thank you. If you have any questions, please feel free to ask.
Thank you, Santiago. I think we already have one question from David Losher in chat. So I can read out. So he's asking whether you are doing the optimization based on the existing scenarios, like the economic landscape or regulatory framework, and do you also do some optimizing under the future changes, for instance, change the energy tax or the new energy performance of the buildings, for instance?
Yes, that's really interesting because what we saw is that the tax reduction impacts a lot of the value of your export PV in the life cycle. So what happens if it stops? Yesterday we were talking with some people from Spain, and they were telling us that happened in Spain, that they were high expectation that the support will continue, but then it stopped. And then many companies went bankrupt. So yes, definitely that's an interesting scenario, and I will definitely consider it now that I'm working on the models.
Yes, good, thank you. Is there any other question? Yeah, Johan, yeah, please.
Yes. I would like to follow up on that sort of line of thoughts on including policy and political aspects into this framework, because what we currently experience is that China has set up a quite aggressive industry policy and goals that they would like to dominate the clean energy technologies worldwide, including PV, but also batteries, electrical vehicles, etc., and giving quite substantial subsidies to their industry to scale up. And this has led to, at least in this PV industry, a situation where the manufacturing capacity along the whole value chain, going from polysilicon down to modules, is twice as big as the actual annual deployment market. So we can produce twice as many modules as compared to what we install, which has led to severe price pressures where module manufacturers are sort of forced to sell their modules below their own manufacturing cost to even have cells and to be able to have some cash flows. And we already now have started to get reports that to cope with this low prices due to a huge overcapacity on a global level, there will be quality issues coming for the modules, that to be able to reduce costs, to reduce manufacturing costs, to cope with the current module prices on the global level, quality will perhaps be reduced in the modules, and that will in the end lead to a much worse environmental footprint, just because the industry is trying to cope with political objectives and are forced into an economic framework where it's they do not make any profit with the current prices. So that's a suggestion from my side to also include what policies and political goals, etc., can have, what kind of effect it can have on the environmental goals. So sorry for a long sort of rant here, but just a suggestion from my side.
Thank you.
Thank you.
Yeah. Do you want to have a response direct to Johan? Or
I think Johan was mostly responding to the previous question.
okay.
But yes, definitely. Different studies, different results. You can get PV according to the studies. 5 grams per kilowatt hour, which is very, 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 very low. Also, you can get up to 120 or 200 kilowatt hour according to other studies. So there's a lot of variation within the environmental impact of PVs. I don't know if it is real or if it depends on the assumptions, but definitely we should address that in our studies with some sensitivity analysis. What happens if we use a PV with higher or lower environmental impact? So yes, we are doing that already. Thank you.
My point was actually to look between the connection of how to say, political industry goals and currently how that seems to lead to lower quality of the modules, which will have an effect on lifetime and then on environmental issues as well.
Yeah, thank you. So that sounds more like an interdisciplinary approach. I think I cannot address this in my model. So we will try. We have some interdisciplinary areas around, so we can ask around if we can build teams for that.
Yeah, thank you a lot, Johan. I think it's definitely connected with optimization. I think it's also a question of being also discussed across different themes, especially in theme 7, that for the sustainability issues. But yeah, thanks a lot for the comment. I think it's a very good one. Anyone wanted to respond to that? Joachim Kumar?
No, I just want to say that I think it's a good thing that you're mentioning it, Johan, because it will affect the trending of this. Santiago is sort of checking this to current state of the art, I guess, and then what happens ahead, it will affect this. Yeah.
Perfect. Thank you. Then we are on the track on this agenda. So then next speaker will be Reza. Please, if you can share your presentation.
Yes. You're seeing my screen, right? And okay, then I'll. Sorry. Just need to. Okay, I hope you hear me well. So in this moment, I'll present this topic. How can PV system alongside wind, EV charging be optimized to enhance the performance of energy systems? I prepare my introduction slide, but I have introduced myself, so we can skip it and we can have more time for discussion, perhaps. So this presentation is based on this paper we recently published. The title is similar to the title of this presentation, but I want to highlight some keywords. So we will talk about urban energy systems, energy matching, optimization, wind power, solar power, EV charging, vehicle to grid. And yeah, you're welcome to read this paper. We'll be very happy. But the intention of this study is to optimize the city-scale energy system involving this power technology, this system, and the optimization method. So I have 15 minutes, and I think I will spend 10 minutes on describing some technical aspects so that you can understand the context very well. So we will talk about urban energy system and their boundary and renewable electricity utilization, which actually Santiago has mentioned a bit. And we will discuss about urban transport electrification. There are several models or several methods. We have opportunistic charging, smart charging, vehicle to grid. And then when it comes to renewable electricity integration, we want to optimize how much solar and wind should we have. And we take a Swedish city as a case study here. And then we want to also compare vehicle to grid to stationary battery in urban energy systems. Okay, so we should begin here. The focus on this study is about urban energy systems, but on general term, we can agree that actually urban energy system is also local energy system. Traditionally, we have centralized power generation somewhere, for example, in the north, and then we just use the electricity from the grid. But now we can have PV, wind, battery storage, electric vehicle, and those are contributing to the local energy systems. So what I want to highlight here is that it's about local energy systems. And in local energy systems, and in this case, urban energy system, we can distinguish three systems. For example, the first one I illustrate with small generation here, with many buildings, illustrating many demands, and we are consuming much energy from the main grid. So this local energy system is net consumer. On the second figure here, we have kind of like a similar size of local generation and the demand. If we consume and produce the same amount, even for example in 1 year, we are considered net zero energy. But in this case, it's not necessarily that we don't interact with the grid. We can still send the extra energy to the grid, and we take energy from the grid if there is temporal mismatch. And then one more thing is the local energy system can be net producer if the generation is higher than demand. So we most of the time send our excess energy to the grid. So yeah, some basic definition. So I will talk about some metric here. And in this case, Santiago has mentioned about self-consumption and self-sufficiency. But in simple terms, self-consumption is, so in this case, we have local generation here, and then we have demand. Self-consumption is basically this part, which is self-consumed PV generation divided by total generation. So it's C divided by B plus C. So it indicates how much PV that we self-consume, that we self-utilize, while self-sufficiency is C here divided by A plus C. So it indicates that how much the solar are covering the demand here. So that's the difference. Self-consumption is C divided by B plus C, and self-sufficiency is C divided by A plus C. And here are format math formulation, but of course, this is not the right time and right place to explain this, but I hope you understand the context. But so what is happening in the local energy system, that if we have undersized local generation, we have too little local generation, so we will have high self-sufficiency because we consume all the generation that we produce, but then we will have low self-sufficiency because this generation is too little to cover the whole demand. So most of the time, we will take the energy from the grid, and we can still send some because there might be mismatch. Like if we generate in the day, we cannot consume all, then we send it in the night. But most of the time, we take the energy from the grid. So the district relies on the grid in fulfilling their energy demands. And in oversized local generation here, the district will have low self-consumption because we have so much excess generation that we cannot consume locally. So we send the extra generation to the grid. That's why we have low self-consumption. But then we will have high self-sufficiency because this large generation most probably can cover most of the local load here. But then there might be some mismatch, like if in the night, for example, we cannot really have energy from the renewable if it's PV, so we borrow from the grid in this case. Then the conclusion is that the district relies on the grid in handling the overgeneration problem. So most of the time, the grid is unhappy if we have excess generation. And actually, at some point, we need to curtail most of the energy production. So in this case, actually, no storage nor load shifting is deployed. This is the base scenario. So I have spent 8 minutes, but then I will introduce you one metric that we invent a few years ago. So we know that high self-consumption will lead, not will lead, but most probably if we have high self-consumption, we will have low self-sufficiency. And the other way around, if we have high self-sufficiency, most of the time we will have self-consumption. Then we are confused which one is more important, because then when you do optimization, you want to have good load matching score. So then we combine this metric to have a new metric, which we call self-consumption sufficiency balance based on a harmonic mean. So in this case, for example, if we have high self-consumption, doesn't mean that we are good at load matching, because if we have at this point, for example, self-consumption 1, self-sufficiency is 0, it's still blue, which is low. The same way, if SS is 1, the self-consumption is 0, we are still having bad load matching. So the good thing is that if we have both self-consumption and self-sufficiency high, so there we can optimize our design, how much power generation should we have to maximize the SCSB. So here is the paper. You are very welcome to read it as well. So then question, what does SCSB of 1 means? That means that the district is both energy and power fully independent from the grid. So no curtailment, no excess generation. The the district doesn't need the grid, so it's a resilient system. It can operate in islanding mode. Okay, now enough with some introduction. In our case study in a Swedish city in the east, we want to simulate also how much impact EV charging can have in the city energy system. So we then define 3 charging scenario, which is opportunistic. EV are charged as soon as they arrive at the charging destination. And smart charging, EVs are charged at the charging destination with the ability to adjust unidirectional charging rate and time, which means that only charging is load. And we have vehicle to grid, also with ability to adjust charging rate and time, but then it can both do charging and discharging. So yeah, here is the example. The top figure here is the net load of the city, and the gray is without EV, blue is with opportunistic charging, yellow is with smart charging, and red is with vehicle to grid. As you can see here that the negative net load means that we have excess energy that we don't consume locally. So for in this case, if we don't have EV, this is the load. And if we have opportunistic charging, we kind of reduce the excess generation here, but then we actually make the peak load worse. And with smart charging, we decrease the excess generation more significantly, but then we don't do improvement on the net load. So there is no net load reduction. It's the same as the without EV, for example, maximum. And with vehicle to grid, we can do both. For example, here we let's say here, then we reduce the excess generation, even it's charged for some reason. But then we completely cut the net load. Even in this case, we have no interaction with the grid. So the city in this case is solely powered by the battery in the vehicles. And also here, see that it reduced the excess generation. Yeah. So now we have optimal sizing. And so in net zero scenario, the optimal wind PV ratio, because we are not sure if we should have 100% PV, 100% wind, or 50-50. But then based on this measure, the load matching measure, we can see that it behaves like this. So 0 is wind here, 100 is PV, and in this case, to the right side, it's 100 wind and 0 PV. So yeah, it's it's a step function here. And we found out that if we don't have V2G, if we only have opportunistic charging and smart charging, the optimal wind PV ratio is 80% wind and 20% solar. But if we have vehicle to grid capability, so the optimal one is 70% wind and 30% PV. And also I want to highlight that without vehicle to grid, the load matching metric is very low if we have 100% PV. Like here, if this is 100% PV, no wind. Yeah, but with vehicle to grid, it's significantly improved. And I just want to show you this figure comparing uncontrolled charging, smart charging, and vehicle to grid. But our time is kind of limited, so I will skip this one. And also, in this case, it was net zero energy scenario, but what is the optimal production to load ratio? So if we have vehicle to grid scenario, then the net zero is the most optimal one. But if we don't have V2G, it is preferable to have less generation local generation compared to the load. So the optimal without vehicle to grid is 0.85, which means that 85% of the generation size is 85% of the demand. That will be the optimal one. One last point. So we also simulate how much vehicle to grid compared to stationary storage. And the conclusion is that 2.4 gigawatt hour EV batteries with V2G equals 1.4 gigawatt hour stationary storage in terms of improving the urban scale load matching performance. So it's similar if we have very big battery compared to if we utilize our citizens' EVs. That's what we want to say. Now it's the conclusion. So the optimal wind PV electricity production is 70 to 30% when we deploy V2G and net zero energy. And in the optimal scenario, we increase the load matching performance from 68 to 73% if we deploy smart charging, and further to 84% in V2G scenario. And lastly, 2.4 gigawatt EV batteries with V2G equals 1.4 gigawatt hour stationary storage in terms of improving the urban scale load matching performance. So here are our partners. Thank you so much.
Good work, Veda. So thanks a lot. Due to the limit time, either we have a very short question or we can leave the comment to the end.
Perhaps I can stop sharing.
Do we have any questions? Very short one. Yes, please, David.
Yeah, very good presentation, Reza. So did I get you right that with vehicle to grid, it is possible to end up with a fully self-sufficient local energy system? And is that then based on what? I mean, I didn't really get how much EVs have you projected to be there? Can you put in EVs in your model, or do you know?
Yeah.
Are you using the existing vehicle fleet? So it's a realistic approach.
Yes, this is very important question, and I don't have time to explain the whole things, of course, but we base our simulation on the existing trend of EVs. If I recall it correctly, it's 10 to 20% of existing demand. So
Okay.
that's the scenario. And of course, we cannot be self-sufficient with these EV loans. Actually, in the paper, we also simulate how much storage is needed to be fully self-sufficient. And it's very large stationary storage, actually. So we are still far from being self-sufficient with renewable alone.
Okay.
Yeah.
Good. Thanks a lot. And if we have more, then we leave it to the last session. Thanks a lot again, Reza. So we move to
Thank
the
you,
next
everybody.
meeting. Mohammed, please, if you can share your slides.
Chin, can you see my slide?
Yeah, we can see it.
Hello, welcome to my presentation. My name is Mohammed Kubar. I'm a PhD student at Uppsala University. I will talk about the solar parks and battery storage in Sweden, operating on frequency market and other market. The agenda for today, I will talk a brief introduction, give some background, go directly to the aims and our case study, method and the key result, and finalizing this conclusion and the future work. I want to start from a very basic idea that going in this energy transition, we moved from centralized power production to decentralized distribution, as Reza has mentioned, the electric vehicle, battery storage, and photovoltaics. And the increase of installation of renewable energy and the delay of investment in the power grid, we need more flexibility to keep the frequency 50 hertz. So I want to link it to what Reza was talking about. Maybe it's important to increase battery storage for doing flexibility in the system if we cannot go to 100% self-sufficiency from renewables. And we should use this flexibility in correct way if we want to go to high share of renewable on high level scale and counter level scale. Battery storage has shown a very decrease in the prices since the last 10 years, around 90% to 80% decrease in the prices. And in addition, it has been predicted that the increase in the installation of battery storage will be in Sweden, 2 gigawatt hour or 4 gigawatt hour, depending on different forecasting, European or local new technique. And if we want to put the battery storage in the context of solar energy and in the context of the size which we operate, if it's a PV park, a photovoltaic solar farm, or it's an industrial load, we can see that the battery can give a lot of services to the owner of the solar park or the owner of the commercial load or residential load. I put here some example going from energy arbitrage on electricity market or spot market, frequency market, increasing flexibility in the distribution system operator on the bottlenecks in local energy market like Stockholm Flex. In addition, limiting the curtailment of this renewable energy which we generate from the PV farm, or for industrial, decreasing the electricity bill by doing peak shaving. So moving to this is a little background about my topic and what I'm going to say about the aims. So what we have thought about is to create a techno-economical framework for solar parks and combine it with battery storage, and see if this battery storage operate on a frequency market and on electricity market, what will be the economic and technical outputs from this operation and this framework. So this is was the focus, and the main point here is that we have this framework, and if we apply it to Sweden or we apply it to other country, also it should give us about how this combination will be and what is the economical value of this battery storage. For the Swedish case here, we used some data from Uppsala solar park in Fyrisland, which is owned by Vasa Kroner. And another aim, so this was recent work we have done on solar PV parks. Another aim was to see for commercial load, like the Church of Sweden, if operating this battery storage for peak shaving, in addition adding some flexibility on local energy market and maximizing self-consumption, as well as arbitrage and the frequency market, so using all possible operation. And we had a case study from Karlstad, Killa Church. And the goal also I want to mention is that the Church of Sweden put some goals in 2030 to achieve sustainability. So this was one of the aim to investigate this installation of the battery storage in the church. The method we have used, it's a combination of energy management for the battery storage with some optimization technique. Santiago have mentioned some key performance, and this is when we use optimization. So we get some economical factors like not the present value or payback period. And when we look also to the technical aspect of the battery degradation. And there was other metrics, but I put the key elements which we have investigated. Now the input for our model it's real data. We have used real data from electricity market, PV production from the cases which I have shown, as well as frequency data of the grid, Nordic grid, which we are connected to. And also we installed this simulation model and import our battery parameters for dependent on each case study. A little bit before going to key performance and key result, I want to tell about a little bit about the frequency market and the way of simplifying how it works. It's connected to Svenska Kraftnät, and it has different services, but it's all like different way of transportation. Some of them are fast, have high response time, and they have some of them are automatic, some of them are manual, and they have different operation range and different activation rate. And our focus was on the primary frequency reserve and the fast frequency reserve, which is in the red box. So some of the key results we showed in this work that when we have the battery storage, the economical value is high and has been increased from 2021 to 2022, and the 2023 was also high. And on the top left, it's the legend where we show the different service, which I have mentioned. FCRD is for disturbance operation, and FCRN in normal condition. And we see that the operation on FCRD have been more beneficial from the optimization model, and the value of the battery storage was around 8 million Swedish crown per megawatt hour during 2022 and 2023. We get a step further and we implemented the same model, but we imported the data from Germany. And we have seen there's a big difference on the revenue. For example, in arbitrage, when operate in electricity market, the German case has more revenue than the Swedish case. In the opposite side, when we optimize to operate on the best markets, we can see in Germany the optimization pick almost equal value. So the value of optimization is very high. It's very high in Germany. However, in Sweden, the operation is just operating on frequency market will give you a lot of revenue. The arbitrage value is low, and it's 4 times higher in Sweden when we operate on multi-market operation. I will move to the church case study where we investigate adding the battery storage, and we have selected all the possible scenario of the operation, and I would say there's no economical feasibility other than including the frequency regulation market in the operation. If you want to just operate on local market, it's not feasible. If it's only on energy arbitrage, it will not be feasible, economically feasible. And also the other, we should include the frequency regulation market in the operation. The payback period was 1.6 years when we investigate the size of the battery. And I want to mention also that this battery storage has been installed and now start operation. It was in the pre-qualification phase before summer. And finally, I will give some conclusion of this 2 work. So the economical value of battery in Sweden is high due to ancillary service. And we have seen loss in energy between PV parks and battery storage when operate on FCR. The degradation is low because the FCRD, it doesn't operate very high. There's low cycling on annual level. And the battery storage is beneficial for the church economically, especially if operating on frequency regulation market, environmentally when we work on self-consumption and maximizing the self-consumption, and socially to provide service to society which the church located in. I want to point also to some future work where Svenska Kraftnät has published. There may be increased in the need for these services and other services which will be automatic. So I showed that some are automatic and manual, but there's a project now to make all the service automatic. So the secondary reserve and territory reserve will be all automatic. Including this service in the framework will be have a high potential to give a conclusion about including all the services in the frequency market, and also enabling the electric vehicle battery storage to give more flexibility to the power system will be very potential, and we need it if we want to increase renewable in our society. This work is has published, some of the articles has published, and if you have any question, just get back to this to us, and I'm happy to give further detail about the analysis. I want to thank the team at Uppsala University, my supervisors, Joachim and David, and my co-worker also Oscar Lindberg, and from Dalarna, Bei Huang, and from Vattenfall, Magnus Berg, and also Svenska kyrka and Varsakron for the availability of the data and the fast response and giving the data for applying this analysis. And thank you for attention, and happy to answer if you have any question.
Perfect. Thanks a lot, Mohammed. Do we have any one or two short questions so far? Okay, if we, yeah, yes, please, Dennis, Ona.
Yes. Hello. Oh, maybe we should do it. You're sitting here with a recording watching, so there was an echo. Sorry about that. Could you please explain a bit more the point you had about the low synergy when combining PV parks with battery storage? What was that due to? Was it the connection size that didn't allow good penetration, or what was the reason behind?
Yeah, when we operated on the optimized scenario, when we operate on FCRD, the battery has very low discharge operating on FCRD. So you don't want to recover much to charge from the PV. So, so operating the PV, the battery utility scale will not charge much from the PV because it's very low discharging and low charging and low cycle. But we want to investigate more the other ancillary services in a real-time model. So operating on secondary reserve or MFRR, and here the discharge will be higher. So of course it could have some potential, but here's a focus on the primary reserve and on the optimized case, which is the FCRD.
Yeah, but so you could say that the battery could reap the same benefits, or could it not?
Yeah, it could gain the same benefit if it's connected to the PV park or it's not connected to the PV park.
Okay.
Good. Thanks. Yeah. And then due to the limit time, then if we have a further question, we go to the final section then. So let's welcome Andreas. You can share your slides as a final speaker.
Request to share my screen.
There's one more question, just I guess, or you want to take it at the end?
Let's see.
It's okay by my side.
Yeah, maybe it's easier to take it now, Mohammed, if you can.
Yeah, FCRN is a combined service, so it's for both up and down. So if you bid in FCRN, so you are obliged to operate on up and down. So it's symmetrical service. And also there's possibility to combine it with FCRD up and down, but you have to obey the technical requirement, which you can find, I think, on the website of Svenska Kraftnät, and you can see how much you have capacity. They have an application. You can see how much you can operate on FCRN alone, And if you want to combine it with FCRD up or FCRD down, you can find all this detail. And if you have any question, please feel free to send an email and I can send you the links and give you other information.
Perfect. Thanks a lot. Yeah. Mohammed, if you can end up your sharing.
Yeah.
Yeah. And Andres, yeah, please. Can you go to the presentation mode? The slide.
Yeah. Is that okay now?
It looks a little bit smaller. I don't know what, but it should be fine, I think.
Maybe it is. Yeah. Okay. Shall I start? Looks okay. Are you hearing? Do you hear me? Okay.
Yes, we can hear it.
Okay, I'm going to present how can data analytics and modeling provide information in smart grid energy saving on behalf of Phil Opke, who is a PhD candidate at Kassel University. This is Phil Opke. Actually, always Phil Opke starts with this photo, which is his twin brother, but Phil Opke looks like his twin brother. So he joined Kassel University in 2020, Phil, as a research engineer. And when Solve Research Center started, he continued as a PhD candidate. His background is in computer science. So as an overview of the abstract level presentation today, we are going to explore the role of data analytics and modeling in modern energy systems and the relevance of smart grids in enhancing energy efficiency and stability. The objective today is to highlight how machine learning predicts energy production and consumption and how these forecasts can be used as an input for optimization of renewable energy communities or renewable energy-based energy grids. About the role of smart grids in urban energy systems, I'm going to start with the definition as given by Phil, that is quite to the point. As a smart grid, one can think that is an advanced energy network that utilizes digital communication technologies in order to be capable to detect and react to local changes in an energy usage. So that means that the importance of smart grids is one can use this smart concept with advanced digitalization in order to integrate more and more renewable energy. We have already seen 3 presentations quite to the point on how to integrate renewable energy in the presence of other technologies like electric vehicles, batteries. So this can be used as an input to optimize the energy distribution and consumption, aiming to reduce waste, minimize the energy losses, and of course, help to grid stability. What are some of the basic challenges in an urban energy management system? One can start on talk about the energy balance, how to meet the energy demand, and by using renewables that their productions fluctuate, like for solar power. And the second is how to improve the grid stability, energy efficiency under all these strongly variable operational conditions. So one can say that we need to optimize the energy usage and to make it in a way that one can also save energy for other purposes, like, for example, frequency-related stability issues. What is the role of data analytics in energy systems? We focus on data-driven decision-making. It means that we collect data, we treat data in a way that one can derive some information about the operation of the system, the nature of the system, not how the system looks like as a physical model, but how does this behave. So this gives us the opportunity to make the correct decision according to the operational circumstances. To make it more, to narrow down this concept in the smart grid, and as regards Phil's PhD project, we are talking about forecast of energy production from renewables, mainly solar at the moment, forecast of energy production patterns, and this gives an input on finding ways, opportunities for energy saving. Phil applies machine learning for his forecasts. It's a technology, machine learning is a technology, we can call it technology, where one can learn from data to make accurate predictions. Why machine learning? Because it can handle the new technologies, complexities. Machine learning can handle complex and non-linear relationships. So we can apply this to energy production and energy consumption systems in order to provide predictions that offer higher accuracy and mainly adaptability. That means one has the opportunity to improve the models easier, the accuracy of the models much easier in comparison to more traditional methods like, for example, physical models of solar power, for example. So one can think as the machine learning process as a black box, or where you send this black box data. For example, when you want to forecast the solar production, you send data about solar production, meteorological input, and then you have as an output the forecasted PV power production. On the screen, maybe I can use just a typical first level result forecasting the power production from a PV is, as you see in this picture, where the actual data is the blue ones and the predicted data are the red, whatever color it is. But let's continue to the next one and talk about the prediction of energy production consumption with machine learning. A step further, what are the benefits of predicting photovoltaic power production using machine learning? At first, as we have said, it is that it helps to integrate more and more photovoltaic power in a specific point in the grid. This gives us the opportunity to produce as much as we want. This is a big question mark on how to do it, but this is another discussion, but we can leave it on the side at the moment. How much power we can produce in order to leave the backup power resources on the side. And we can use them in cases that we have some other problems, like, for example, the ones that Mohammed presented us in the previous slide, when we have a frequency-related operational issues. As regards the energy consumption, one can say that the benefits is that we can enhance the energy efficiency because we minimize the waste. We can involve demand response strategies behind the meters. So the end users themselves can adapt their needs according to what the availability of power production is. And this gives an opportunity to further improve the grid stability. Some other results that Phil produced are shown in these two figures. On the left side, you see the produced power from a PV solar PV system, where the thick black line shows the median value, the mean value. And with blue, you see the under prediction. It appears that maybe we can produce less. Or with the orange, or light brown, you can see the over prediction. So, for example, at 10 o'clock, this is what we expect, but it might be more or less. These upper and lower boundaries play an important role on the optimization of the systems and how one can apply methods to integrate electric vehicles, charging, grid to the vehicle to the grid, support, and so on. This is on the right side, you see a similar prediction about the power consumption. And you see once again that we can predict the this is not over consumption, it is over prediction again. It means that we might have more production, consumption or less consumption. These two inputs are very much important for the optimization of systems and how one can utilize more efficiently energy. I think I have to be a little faster here. Some other examples from prior studies is, as I said, power production from PVs. Here is a sunny day where you see the power, the prediction is quite good. And here is a heavily overcast day, I would say, where the blue are the actual values and the predicted are the red ones, where one can see a good match. But further on is something that we call machine learning model drifting. It means that there are occasions where the behavior of the system changes because of some reasons. In this case, the predictions based on the historical data start failing. So the predictions are not so accurate. This is called machine learning model drifting. A typical example is when you have a house where, in the first instance, you had 3 people living in a house with 2 computers and some facilities and so on. And then some other people use the house with different habits and different daily consumption patterns. In this case, the historical data from that house do not produce proper forecast about the energy pattern for the new habitants in the house. This is something that we also solve with machine learning. Machine learning is a nice way to overcome these difficulties. And this is something that the field is still working on. So, to conclude, we have some minutes for further discussion. The challenges in order to implement all this data-driven decision-making in smart grids about energy issues is, of course, data quality. We need high-quality data in order to have reliable predictions. On the other hand, we have also to improve the machine learning models that we use in order to have high predictions, not only the data that we use, but also the machine learning model that we use and how you can improve it. And a third challenge that is also quite heavy in the picture, I would say, is how to integrate this concept of collecting data, using data, making predictions, giving to a system that runs the optimization of the energy systems and then gives the decisions back to the system itself to adapt the operation to the next time window. This is something that is also very much important because we don't want to increase the computational cost, the cost of the facilities themselves. So, in conclusion, and as a summary, data analytics and machine learning are crucial for optimizing smart grids. Actionable insight from machine learning can lead to energy savings and grid stability. And as a final thought from Phil, I would say that we need a continued innovation, which is essential for creating sustainable and resilient energy systems. I hope that I transferred Theo's concept in a proper way. And I would like to thank on behalf of Theo. Any questions, please?
Thanks a lot, Andres. And we have one question from Marcus in the chat. So regarding the weather data.
No, yeah, I can read the question to everyone. Knowing the weather, radiation, wind, temperature, one can precisely calculate the PV power production. Why is historical data needed together with other forecast in the machine model? What improve the weather forecast? Yeah, thank you very much, Marcus, for this question. We have discussed this several times, and indeed, one can provide very accurate predictions by using typical mathematical, let me call them Bayes models. However, there is in some cases there are some difficulties when we talk on system level. For example, for a system operator, it's not easy to have access to the details of the panels that are used in each residential house, wherever they are. So, and the collection of all these data is not something that is feasible and easy. On the other hand, indeed, one can calculate the PV power production from a solar panel or a series of solar panels in any conditions, even in the presence of shadow, for example. However, the shadow can change from time to time. Things can happen. The panel on the top of the panels won't be very clean or whatever. So all these problems disappear by using machine learning because all this information are already in data.
I understand. Thank you. To summarize, I understand that this historical data is needed to get more information about the physics of your PV system.
Yeah.
Okay.
The conditions, I would say, the physics and the conditions that appear periodically from time to time and create the pattern.
Mm-hmm.
Oh.
Thank you.
Thank you, Marcus.
Thank you. We have another question from Johan Linda.
So, as I understand the field, there are this physical bottom-up modeling, and it's statistical, in many cases, machine learning modeling to predict the PV production. Would your machine learning models benefit from more technical data, and not only the historical power production?
Yeah. I think you're talking about physical informed machine learning concepts that appear recently in the literature. It is something in between that we discussed with Marcus previously. Indeed, by knowing some key physical properties of the solar panels might play not important, but an essential role on how to improve the accuracy of the predictions. Like, for example, how much the voltage or the power changes when you have one great change in the temperature, some coefficients that include in the technical specifications. We haven't used this technique so far. Maybe we can use it in the future. So I cannot tell you from our own research what will be the benefit, but according to the literature, physical informed machine learning models appear to have some improved accuracy.
Because what I understand, the main problem of physical models so far has been a lot of lack of technical information, and one of the major one is that there's usually no data on the orientation. But through remote sensing, and that's actually research that I'm involved in, we can calculate and drive the orientation of all PV system in a municipality, for example. would that kind of information on the orientation be beneficial for your model? And in that case, perhaps we can talk after this meeting.
Yes, yes, for sure. Exactly. This is a very nice and helpful suggestion. Thank you, Johan. We will keep in contact about this.
Thanks a lot.
We have some questions also actually for Kubar. Is he still in here? They're technically in the chat, a number of them.
Yeah, Joachim, I was replying to the chat. Can you hear me?
Yeah.
Yeah, I saw some comments about the connection point of PV park with on the grid. So this is very important parameter when conducting the analysis. In our case study, we haven't investigated the connection grid because also we had another case in Germany where we don't have information how much the limit of the connection point, but it could be a good point to include in the. It could be important to include it maybe and see the difference if we have different connection point in the two cases and see how the sun energy will change in the model.
But I think maybe I could also add a little bit of thing here is that I think the main takeaway is that currently the battery storage, the activation of that on various markets is what gives the most payoff stuff. So it doesn't help that much to have a park. It may help the connection point a bit and so on, but it's the battery storage that's so dominating currently for Sweden.
Well, thanks a lot for the elaboration. So yeah, because of the time we have to run off. So one last slide from us is the summary, and I'll probably also for the discussion that I want everyone to bring home. So I just list all the questions and the comment that from the guests. So so if you have additional comments or discussion right now, so feel free to have to propose, because otherwise we will share the slides together with this summarized comments to everyone. So, and basically we have questions on the optimization of different scenarios, both in existing and the futures, and also especially the political scales influence, especially on the environmental objectives optimization. And then we'll also have comments about the EV capacity, how that is big enough, to reach a net zero scenario. Then we'll also discuss, like just now happened, about the technical optimization, where we have to see more elaboration on the optimization of the battery service for the grid. And then a few questions regarding this historic weather data and also with the forecast data into the data-driven model, and also benefits from the technical data to improve the accuracy of the data-driven models. So I think it's quite a mixture of the or response to our presentation today. So from my side, I think I don't have any further comment to continue. So if you do have, either leave us a chat, comment in the chat, or just feel free to hand up in 1 or 2 minutes. Otherwise, we will circulate, I think, the presentation to everyone after the webinar. So if you still have questions, you can either contact us or contact each presenter for a detailed question. All right, so any further or last question or comment?
Just to thank them for being here. Really. Thanks, everyone.
All right, so then we'll stop sharing right now, and then thanks a lot